Be held from first.
dpktu@ktu.in.
இது அனுப்பணுமா அல்லது இந்த இது அனுப்பணுமா? டாக்குமெண்ட்ஸ்.
Sir,
good morning. Kamalakannan, I am audible?
Yes, yeah, sir. Is it audible?
சார் நான் பேசுறேன் எனக்கு கேட்கல. உங்களுக்குலாம் கேக்குதா?
ஹலோ கொடுங்க.
வரல.
Sir, I am audible, sir?
Yes, sir. Yes, audible.
Yes. Fine, sir. So, shall we start at 11:30, sir? Sharply. நீங்க வேணா ஸ்கிரீன் ஷேர் பண்ணி பாத்துக்கிறீங்களா கமலக்கண்ணன்?
Yes, sure, sir. Yes.
போயிட்டு அந்த என்டையர் ஸ்கிரீன் ஆப்ஷன் ஒன்று இருக்கும்ல, அது வழியா வந்தீங்கன்னா தான் ஈஸியா இருக்கும்.
Okay, sir, sure.
Really?
Yes. இப்போ ஸ்லைட மூவ் பண்ணுங்க. ஒர்க் ஆகுது, கரெக்டா இருக்கு, சூப்பர். 11:30 ஸ்டார்ட் பண்ணிடலாம்.
இல்ல சயின்ஸ்ல SCIE
சார்
சயின்ஸ்.
சார் நீங்க மியூட் பண்ணுங்க சார், உங்க வாய்ஸ் பேக்ரவுண்ட் வாய்ஸ் வந்துட்டே இருக்கு சார். எஸ் சார், தேங்க்யூ சார்.
Yes, sir.
Kamalakannan, shall we start by 11:30 sharply?
Yeah, sure, sir. Yes, sir.
Okay.
Yes.
Sir, shall we start, sir?
Yes, sir. Yeah, warm welcome. Once again, get it. Sir, my voice is audible, sir. Sir,
Yeah, yes, sir.
sir, my voice is audible, sir. Sir, audible. Okay. So once again, I welcome you all for this it's a wonderful session. So I hope you people are enjoyed the previous session, right? And today also, so now we have a eminent personality, right? And at another session, there is a national workshop on density functional theory. And first of all, I would like to welcome our resource person, Kamalakannan sir, a post-doctoral researcher from Incheon University, Republic of Korea. And next, I'd like to welcome the HO of various institute and head of the departments, principal and vice principal, sir, and my dear colleague and students, friends. To start the session, I want to give us some brief about the density functional theory. In the recent days, people are working in supercapacitor applications. So many the people are struggling with the HER mechanism, the hydrogen evolving reaction mechanism. The actual the limitations for HER mechanism and HER mechanism is bicatalyst and also bifunctional mechanism. By using this density functional theory, we can easily solve this issue, HER and HOR issue, and also mainly the top layer and then the hollow layer involvement. That's confusion will be easily solved by using the density functional theory. So I hope you people will gain more knowledge from this national workshop, density functional theory. So before start the session, I want to give a short bio about our chief guest and chief guest for this national workshop. And Shah completed UG degree from a PhD College of Arts and Science, Bharatiyar University, and also added the master degree from Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Bharatiyar University, and completed his PhD, followed by it on the title of Electrocatalytic Activation and a Conversion of a CO2 at Ionic Liquid Decorated AU Surface. A computational perspective, mainly. Obtained a PhD degree from SRM Institute of Science and Technology, Chennai, and also completed the short postdoctoral research in the same institute in the title of a design and development of a materials for catalysis, fuel cells, thermoelectrics, sensor, and solar cells and application in the year of 2022. So now also the SAR involving in the postdoctoral contract in the lab of Professor Heng Chul Ham started abroad at Inha University, South Korea, which is still ongoing today. So focusing on the subject of model and efficient catalyst material for HER and a CO2 conversion reaction. So there's a short brief about our guest person. Okay. Sir, once again, I welcome you, sir. And the session is yours, sir.
Yeah. Thank you, sir. Thank you for your nice introduction.
Mm.
So first of all, I thank the coordinators, Shakti Pandian, sir, Professor Shakti Pandian, and co-convener and conveners of this SRM Institute. to inviting me for this next workshop on density functional theory. So next I move on to the foundation of density functional theory. So as we know that the first method that is developed to study the material property, the computational theory developed to investigate the material properties, that is the Hatchcock theory, that is mainly based on the many body wave function. However, this many body wave function is fails to calculate the material property, and also it consumes large time. This is mainly due to the coordinates of all nitrogen atom in the system. It will calculate all the nitrogen atom, all n atom in the system. So, based on this limitation, the Hohenberg and Kahn proposed the density functional theory. This is mainly compute the system property and the molecule material at the atomic scale. So we have to know the what is mean by density and the functional and the theory. So the density, which means this is a central quantity which being computed and manipulated, is not based on the wave function, but it is mainly based on the electron density. And the functional, which means that the central operator, which are the functional, that is the object which will take the function as the argument and return the number as the output. So the theory, because it's science, so we call this is theory. Things is theory. So these two people, they have proposed this. The property of the system can be calculated by the density, not with the wave function. Due to the limitation of wave function, they have proposed the density itself can calculate the ground state property of the system. So um, in this case, the total ground state of the many body electron system is a function of the density. So if we know the electron density function, we can know the total energy of the system. In the DFT, first criteria is to find out the density. So first criteria is to we have to find out the minimum energy of the system. So if we take the material, so first we have to know the minimum energy. So this density functional theory will compute the minimum energy of the system. So next, with this short introduction about the density functional theory, I move on to the research topic, which is done by the first principle approach. That is the topic of this research is the organic acid functionalized GC3 and 4 heterogeneous catalyst for the efficient biodiesel production applications. The before starting into the main results, I would like to introduce some importance of this research. So nowadays, we are consuming more petroleum-based fuel, which is increasing due to the economic development and rising the population of the world. So this biodiesel and the bioenergy, which is mainly becoming a subject of potential interest, because the depletion of this fossil fuel reservoirs as well as the various environmental issues. This biodiesel is also known as the fatty acid methyl ester, which is the mainly the renewable green fuel that has been accepted globally as the alternative fossil fuel, and also it is renewable, non-toxic, and the clean combustion properties. This biodiesel is produced mainly via esterification and transesterification process of vegetable oil or animal fats with the methanol as the suitable catalyst. In recent years, the great attention paid to the development of heterogeneous catalyst because it is an excellent property such as environmental friendly and the catalyst separation as well as the reusability. With this motive of this heterogeneous catalyst, we have with this motive of this heterogeneous catalyst, importance of the heterogeneous catalyst, we have designed various acid doped heterogeneous GC3 and 4 based heterogeneous catalyst. The acids which are we doped is the SO3H and H2PO4 and the COOH and the OH and the gallium OH and the AlOH. So first thing is to confirm is the stability of the system. So in order to know the stability, we have the stability can be identified from various computational descriptors, such as binding energy and formation energy and dissolution potential. Here we have calculated the binding energy of the organic acids over the GC3 and 4 catalyst. The calculated binding energy of these acids with the GC3 and 4 catalyst is more negative. for all the investigated acid dope digitation-4 system, which confirms that the acid dopant over the catalyst is thermodynamically more stable, which will be more suitable for the further application. So also here we can see the calculated bond length between the dopant, acid dopant, and the GC34 is around 1.85, which confirms its strong binding. So furthermore, we have calculated electronic structure analysis to understand the more insights into the bonding behavior between the behavior between the acid dopant and the GC3 and 4, and also the electronic property of the system. So here this is the amber list 15 catalyst. This is the we consider this as the pristine catalyst. The calculated binding energy of this pristine is around 4.1. However, in the acid doped GC3 catalyst is calculated binding energy is around 1.0. This is mainly due to this carbon 2p orbital and N2p states appears above the conduction band region. So which reduces the energy gap, and also this reduced energy gap will enhance its absorption properties, and also the electrical conductivity also will improve and improved. So this electronic and catalytic property improvement, which is clearly identified from this density of states analysis. Also the bonding between the active sites of this organic dopant and the carbon and nitrogen atom of this G3N4 catalyst is clearly identified from this orbital overlap in the valence band and the conduction band region. So furthermore, we have calculated the electron density analysis of this organic acid doped system to understand the how this bonding is bonding nature between the how this organic acid dopant is bonded with the catalyst. So here we can clearly see that there is the strong orbital overlap between the organic acid and also the GC3N4 catalyst, which confirms that this organic acid is strongly binded with this catalyst. And also we can see that the calculated charge over this organic acid dopant is more for ALOH when compared with the other systems, which confirms that this ALOH can provide the superior activity for the incoming molecule actually. So further, next step is the here we have investigated in order to know the acidity and basic property of the material. We have introduced CO2 and NH3 and NH3 into the system. So here the CO2 is stabilized with this catalyst through long range dispersion and also the stronger hydrogen bonding interaction. So the calculated binding energy of the amber list is 0.09. However, it is increased to 0.65 over the COH doped system. So, however, the electron accepting nature is poor. So it confirms the weak Lewis acidity of the catalytic system. However, in the NH3 NH3 incorporated system, this NH3 is having stronger interaction with the uh, catalyst system through stronger hydrogen bonding as well as the weak van der Waals interactions. So the calculated absorption energy of the amber list is 0.12. However, it is increased to around 0.8, 0.9, which confirms that the enhancement of the Lewis acidity of the material. So with this with this enhanced Lewis acidity of this material, we can use this this designed system for the biodiesel production. So before getting into the uh, reaction mechanism, so we have to know the what here we have studied the esterification reaction mechanism. So before going into the topic of the results, we have to know the reaction mechanism. So first step of this esterification reaction mechanism is adsorption of the free fatty acid over this organic acid OA, which means organic acid, into the reaction medium. So due to this adsorption, there will be the stronger charge transfer from the free fatty acid to the organic acid dopant, which leads to the changing of this carbon into carbocation. Tuning of this carbocation, which will be the active site for the incoming moiety. Next step is the introduction of the methanol into the system. So this oxygen atom of this methanol strongly attack this carbocation, which is activated. So this strongly attack this carbocation, which leads to the formation of CO bond, and this hydrogen atom of this methanol attacks this OH group, which leads to the formation of methyl butyrate and the removal of H2O from the medium. This is the methyl butyrate, which is the biodiesel. So this is the esterification reaction mechanism of the organic acid doped system. So this is the initial state and transition state and the final state. The first step is, as I said in the in this slide, the first step is the absorption of free fatty acid over the catalytic medium, which leads to the changing this carbon atom into the carbocation. Next step is the dissociative absorption, non-dissociative absorption of methanol into the system, leads to the strong bonding between this methanol and the free fatty acid. Next, this in this TS step, there is this transfer of proton from methanol to the OH group of the free fatty acid, and the attack of this oxygen atom to the this carbon atom leads to the formation of methyl butyrate and the water molecule. So this calculated the interaction distances also clearly says that the how it's these intermediates were binded with the catalytic medium. So this functional also we can say that these functional sites can polarize the CO bond of butyric acid, which making it easier for the methanol attack. And also the TS tip of this OH step is the catalyst can strongly interact with the methanol, resulting in the effective activation and reducing the energy barrier. Here, this is that these studies can be confirmed from this potential energy diagram. So the calculated reaction energy for the COOH system is around 0.1, and the H2PO4 is 0.08, doped 0.08. So which is lesser than the commercial catalyst. So it confirms that the thermodynamic stability of the designed catalytic system. Further, the calculated activation energy for the transition state step for the amber list is minus 1.93, which is reduced to 1.0 for the OH doped system, which confirms the kinetic favorability of the system. So, however, here we observed that the very poor thermodynamic performance due to the positive energy barrier observed in the final step. So we have introduced Al and gallium OH into the GC3N4 system. So this is the gallium OH and Al OH decorated GC3N4 system. So as I said in the earlier slides, so the same mechanism observed in the same system. So first the free fatty acid adsorption and the non-dissociative adsorption of methanol into the system, then the dissociation of OH bond and the formation of oxygen carbon bonding in the TS step, and the final step is the removal of water and methyl butyrate formation. So the strong AL-OH bonding in the of butyric acid with the functional site to form the carbon to carbocation, it making it easier for the methanol to attack. So which is confirmed from this potential energy diagram, which is the activation energy is significantly reduced, and also the reaction energy for the ALOH and gallium OH is 0.35 and 0.32, which is slightly higher than the amber list catalyst. It clears that the esterification was carried out more efficiently in the screened ALOH doped system. Also, the activation energy of this ALOH doped system is 1.52, which is significantly lesser than the commercial amber list catalyst. This activation energy, which means the bond breaking, the energy required to break the bond and break the bond in the TS step. So the esterification reaction on the ALOH and the gallium OH doped system are more negative in the final step, which shows the thermodynamic favorability of the system. So from these observations, we clearly identified that ALOH and gallium OH is more suitable for the biodiesel production application. So which is further confirmed from the density of states analysis. Here, this is the density of states of the bare catalyst, that is the amber list. There is no appearance, there is no peak in the near Fermi region of this amber list catalyst. However, there is a sharp peak in the acid doped systems. So the short density near the Fermi level of ALOH system, which favors and improves the catalytic activity, which is identified from this density of states. And also the density of states at the near Fermi region was considerably reduced for other organic doped system compared with the ALOH system. So which confirms that ALOH doped GC3N4 can be the suitable candidate for the production of biodiesel. So finally, the observation and the conclusion of our present research is the mainly the incorporation of organic acid doped into the GC3N4 heterogeneous catalyst can be the uh, energetic barrier of this rate determining step was significantly reduced compared with the commercial catalyst, and also the kinetic barrier of for OH and ALOH doped system can be reduced to 0.90 and 0.40 at the rate determining step compared with the commercial catalyst. And also the improved product selectivity of ALOH doped system was further confirmed from the stronger orbital hybridization between the observed O2P and the acid doped AL3D orbital in the valence band region. Finally, our theoretical screening revealed that ALOH doped system can be the promising heterogeneous catalyst for the biodiesel production application. So first, finally, I thank my Professor Ham, for providing the computational facility to perform all the simulations. So thank you all for the kind attention. Yeah, thank you, sir. Thank you. Hello. Yes, sir. Yeah, yeah, sure, sure, sure. Yeah, sure. Yeah, yes, sir. Sir, binding energy will tells us the strength of adsorption as well as which means, for example, if you take the system, if you got this more binding energy, which means the more negative energy, which means the more exothermic, it is easy to happen. However, it is weaker binding means it's less possibility to happen. That is endothermic. We can say less exothermic. Or if you got the positive binding energy, which means that is endothermic. It is there is a less possibility to happen that react for that reaction is very less probable to happen over that catalytic medium. Here we observed more negative, which means the exothermic binding, which means that it is it's ready to happen, which means the more favorability of the reaction medium. It's more favorable to occur over the catalytic medium, sir. Uh, Sir, hello. Yeah, yes, sir. Thank you, sir. Okay, okay. Yeah, yeah. Yeah. Thank you, sir. Thank you so much. Thank you so much for the invitation, sir. Thank you. Thank you so much, sir. Thank you.